There is a feedback problem there. Mas acho que é só esse microfone, né? Como é que faz para o slide aparecer ali? This microphone has a feedback problem. Maybe it's doing No, hello. Esse aqui, this is one. Hello. We're going to do a little switch of the schedule, start the section a little earlier, but before we start, very important, if someone is wanting to go to the dinner tonight and has not confirmed their name yet, please go to this middle section. There is a lady with a computer there. Give your name to that lady so that we can have a seat for you at the dinner tonight. Thank you very much. So the first talk of the section is from Ji from the Institute of Software of the Chinese Academy of Science.
Okay, hello everyone. I'm Ji from ISCAS. Today I'm delighted to share with you our thoughts and experiences in designing the operating system in the era of RISC-V. So what is the operating system? Operating system is defined as a set of software that manages computer hardware and software resources while providing common services for computer programs. The OS plays an important role in the widespread adoption of RISC-V hardware by providing an abstraction layer between the hardware and the software. The RISC-V is stand out for its modularity. RISC-V's modular design aligns perfectly with the trends in hardware-software co-design and makes RISC-V a promising choice for heterogeneous computing. Supporting heterogeneous processors is essential for a RISC-V native operating system. With the rise of RISC-V, the SRX heterogeneity has gained significant popularity. We define the SRX heterogeneity as a set of processors or cores with overlapping ISA. Each processor must support the same base ISA, which is integer ISA of RISC-V. And each processor can customize different ISA extensions, such as a vector, to accelerate specific tasks. The SRX offers unique strengths over other heterogeneity schemes compared to the single ISA heterogeneity, where different processors are only different in microarchitecture. The SRX can provide better performance energy balance. Compared to the disjoint ISA heterogeneity, SRX can simplify the porting process of the existing softwares. For example, the notable disjoint ISA heterogeneous computing system, the Popcorn Linux, has to run a dedicated Linux kernel for each architecture, and they must implement communication infrastructure among these Linux kernels. So the porting process can be quite cumbersome. How to run programs correctly and efficiently on SRX heterogeneous processors is also challenging. Traditional compilation-based methods are unsuitable for RISC-V heterogeneous computing. This method compiles a binary version for each ISA extensions. So we must produce several binary versions for a program. This method can achieve high performance, but it has high porting effort. It is both infeasible for the developers or the end users to compile the program. This is because the RISC-V extensions are increasingly diverse. So it is infeasible for the developers, the software developers, to compile the program, to pre-compile the program for each extension combination. And it is also infeasible for the end users to compile the software by themselves. This is because the recompilation process is very difficult for the end users. The recompilation generally needs specific compilation toolchains, and is time-consuming. In our evaluation, compile a large software generally consumes about several hours, even with the most powerful computer. Therefore, to tackle the above issues, in this study, we argue that the binary translation through binary rewriting is the most suitable to support the SRX heterogeneous computing. The overlapping ESA makes binary translation efficient. This is because SRX heterogeneous processors share the same base ESA, so we do not need to design a complex mechanism to support the system call translation. And we also avoid the complex mechanism for binary synchronization. The extension instructions that need translation only occupy a small portion of the entire program. The small portion, so we only need to rewrite a small portion of the program. Most importantly, the binary rewriting process is fast compared to the compilation, which needs several hours. The binary rewriting process of the large binary only needs several minutes. And the rewrited binary can achieve high performance because we only need to rewrite a small portion of the program. So now let's look into the detailed workflow of the binary rewriting with a concrete example. Now consider a binary compiled for the base and vector extensions. But now we need to migrate the program to a target processor which only supports the base instruction. So we need to translate or downgrade the extension instructions in this binary to the base instructions. The workflow has 3 steps. We first disassembly the binary, identify the extension instructions that needs rewriting. In this step, we must approximate the extension instructions because false positives may make us to rewrite a piece of data in this binary, causing the correctness problem. The next step, we can translate the extension instructions to their corresponding base instructions. And finally, we embed these translated base instructions into the binary using the technique called binary rewriting. The binary rewriting generally replaces the extension instructions in place in the binary. After replace the extension instructions with the base instructions in place generally may cause offsetting of the subsequent instructions. This instruction offsetting may cause erroneous jumps because the original indirect jumps in the binary will jump to incorrect position, and we must correct this position to the correct position in the rewritten binary. So we must use a control flow recovery to make this binary rewriting correct. However, the binary rewriting in static binary, the control flow recovery in the static binary rewriting is impossible because it is impossible to identify all the pointer computations in static analysis without the runtime information. It needs some data flow analysis, which is a still unsolved problem. Failing to perform a sound pointer analysis during rewriting will cause a correctness issue. So we introduce two runtime method to ensure the correctness of the binary rewriting. The first one is runtime address translation. In this method, we maintain a lookup table where the key of the lookup table is an instruction address in the original binary, while the target of while the value in the lookup table is a new instruction address in the rewritten binary. So when we encounter an indirect jump at runtime, we can refer to the lookup table to correct the position to the in the rewritten binary. The second method is binary patching. The binary patching method avoids the instruction offset at the very beginning. It replaces an extension instruction with a triplan, which is a single jump instruction. The triplan will redirect the control flow to base instructions at the tail, located at the tail of the binary, so it will not offset any instructions and keep the layout of the binary. However, this method also has limitations. Because a single triplan in RISC-V can only reach a very limited distance. In RISC-V, a single instruction triplan can only achieve a jump range of 1 megabyte. So for long distance jumps, we must use the trap-based triplan. Instead of inserting a single jump instruction, we replace the extension instruction with a single trap instruction as a triplan. When executing the triplan, the program will trap into the kernel space, and our system runtime in the kernel will redirect the control flow to the target instructions. This trap-based triplan will cause much more performance overhead compared to the instruction-based triplan. These two methods for ensuring correctness at runtime is suitable for different kinds of binaries. The binary regeneration costs about 30% overhead for both small and large binaries. And binary patching costs a very small performance overhead for small binaries, but will cause extremely high performance overhead for the large binaries. So in our system, we will use the binary regeneration for the large binaries and use binary patching for the small binaries to achieve a small runtime overhead. To perform the binary translation, we introduce a learned binary translation technique. The RISC-V has a wide range of extensions. The modular design of RISC-V ESA has enabled the rapid growth of domain-specific extensions such as vector, matrix, and crypto. So manually, binary translation rule writing will be infeasible for RISC-V. This is because one RISC-V extensions can introduce hundreds of new instructions, and there are plenty of new extensions. So we develop a learned binary translation to extract the binary translation rules directly from existing binaries. Our technique has 4 steps. In the first step, we compile the same source code, for different ISAs. We use a compiler info to find and match instructions across binaries for different architectures. The second step is generation. From the match, the instruction pairs, we extract mappings between registers, memory, and intermediates to form rule templates. In the third step, we use an SMT solver to check whether the above templates are correct. We mean when the source and the target ISA in the template has the same semantic, we will keep them, and we will only keep the correct templates. Finally, using these templates, we can use these verified templates to translate source ISA binaries into target ISA binaries automatically. except in the above slides, we already introduced how can we migrate a program among different heterogeneous processors. It is also important to make smart migration decisions. To achieve this, we design a safe and efficient task scheduling technique guided by the binary properties. We use the binary properties to get task scheduling. For example, we can achieve parallel execution for program boundaries with commutable operations. And we can achieve precise resource allocation for deterministic programs. The key challenge in this process is a partial boundary visibility, because it is fundamentally impossible for the static analysis to extract all the execution passes of the boundary. So we can only analyze a part of the boundary, and we can only know a subset of the boundary's behavior. Some control flows or instructions may remain hidden or unanalyzable via disassembly. To tackle this problem and ensure correct execution despite the partial analysis, we annotate the analyzable regions in this binary to distinguish the analyzed code. And at runtime, we speculatively execute the programs, assuming all the programs will execute the analyzed portion. We also trace the execution passes of a program at runtime. When the program executes the unanalyzed portion, we will safely handle the unseen or unanalyzable passes safely using techniques like the speculative execution or incremental analysis. Okay, in this talk, we discuss a problem about how to build an operating system that achieves user transparent, correct, and high-performance RISC-V heterogeneous computing. We use binary translation for cross-processor migration, and we use learned binary translation to automatically learn binary translation rules. And we use the binary analysis to make scheduling decisions. Our ultimate goal is to build a Rosetta for RISC-V. We will bridging the gaps between the application and the underlying processors. Any boundaries can run on any RISC-V processors with user transparency, safety, and high performance. Okay, that's all for my presentation, and I'm happy to take questions.
Excellent presentation. I have lots of questions, but I'll let Guido go first. You might be asking the same questions that I would.
Let's see. Thanks for the talk, very insightful. Could you please go to your slide 14, please? Slide 14. Oh no, it's just position in the question. Okay. You mentioned that in your first red block there, you have a compiler acting and generating code for the target ISA and the source ISA, right? Mm-hmm. And you said that you match on number 2 the semantics. How do you do that? I mean,
okay,
because they're very different binaries, right? And you can have scheduling across the semantics of the original source code for the compilers. They may behave differently for different ISAs.
Okay, thanks for the question. Because these two binaries are compiled from the same source code. So we can use the compiler information to identify the instructions that corresponding to the same line of code.
Yeah, but it could have optimization with reschedule code across the original source code, right?
Yes.
So if you turn 03 and you have code, for example, some optimization could go across basic blocks and mess up with your original semantics somehow, isn't it?
we use because we can do the compiler to insert some helper information to insert some hints in the binary. So without these hints, it may be much more difficult to match the instructions.
Okay, but the hints also are fed to the optimizer, right, to avoid scheduling code across, right, somehow.
When you encounter such cases, we will speculatively put these pairs to the candidate rules and verify their consistency later using the SMT solver.
Okay.
This step can be not much concise. It will tolerate false positives.
Okay, got it. Thank you.
Okay.
Other questions?
This approach is used to turn extension instructions into the base scalar instruction. The other way it's possible to turn into the base ISA into the matrix extension or the vector extension.
You mean how to translate the base into matrix?
Yes, just compile the binary, compile into the base instructions, and if you have a processor with an improved extension, you use this extension with those techniques.
We generally support both instruction downgrade and upgrade with existing translation rules.
So I'm going to repeat Rodrigo's question because that was one of my questions. So you have base plus X into base, right? That's the example that you did. So I have the base RISC-V instruction plus X in the binary, and then you want to generate a binary that only has the base. That's what you described in one of your slides.
We do not translate the base instruction. We only translate the extension instructions. In this
Yeah,
case.
so you have base plus X, you transform into base. The question is, can you do base into base plus X? If I have a new RISC-V implementation that has a new extension, and I want to take the binary that was generated for the base set of instructions.
We actually extract the translation rules from the compilers. So if the compilers can support the new RISC-V hardware, we will extract the advanced translation rules from it.
Okay, so I want you to encourage you to think about that, because if you want to build the Rosetta for RISC-V, so we did, the reason I'm familiar with this is because a couple of years ago we did this work for IBM, where you wanted to be able to use the new features, in their case of the power architecture, in a binary that was generated for an old version. So as you introduce new features to an architecture, you like legacy binaries to benefit from that.
Yes.
So I would encourage you to think about supporting, introducing new features into an existing binary.
Yes.
Okay. Any other questions? Oh, over here. Sorry, it was hard to see you here.
I have two questions. The first one, how much time did you spend on this?
It generally takes several hundreds of seconds to learn the translation rules. And the translation process is only several minutes, even for the largest software.
So, you in one of the slides you mentioned LichPy 4A. It was one of the boards you made this, right? Okay. So, do you have these slides and maybe the way you measure the time it's spent in some places, so someone can access and see how did you tested it. We have a repository for this.
I didn't hear clearly. Yes, yes. You're under review.
Okay, so thank you. I just want the link for the paper.
Okay, any final question? Yeah, one more.
Hello. Thank you for your presentation. What I would like to know is if you have this code, it's called Rosetta, right? Yeah, if you have it in open access, if we could use it or not. And to understand, if I understood correctly, you have to do it for each pair that you are doing the translation, right? And it's like a training with AI, and so it would you will have to do all this translation work to all the possibilities, right? The combination possibilities. And what do you have already done for which instructions, translations? How is it?
Okay, we do have open source code, and we will release the code after, because the paper is still under review, we will release the code thereafter. And we currently did not introduce AI techniques in this translation, in this learned boundary translation. But in the future, we plan to use LLM to extract the translation rules, the candidate rules, and use the more rigorous SNT solver to verify their correctness. We currently mainly designed, evaluate this approach on the floating point extensions and the vector extensions.
So just one last question. So given that you're doing this template-based, how are you handling translations from strongly ordered memory models to RISC-V? Or how would you handle them? Because we're having various memory models out there, and even in RISC-V, we're having total store ordering as an extension versus our regular weekly ordered model. So what is the strategy for translating when you're translating between two different memory models?
The question is about the memory consistency models, that there are different models of memory consistency in RISC-V.
Our system do not consider the memory consistency model because we assume different RISC-V processors has the same model. And this is why the binary translation will be efficient for RISC-V heterogeneous processors.
So this is basically just a limitation. You're just assuming it, but it could happen in reality, and then your tool just is going to ignore that case.
Yes, that's correct.
Okay, thank you all for all the wonderful questions. Other questions during the coffee break, we're going to move to the next presenter. You can come up. And keep up with the questions like this. This is what makes so thank you to the speaker. While Yanin is setting up, I forgot to introduce myself in the beginning. I'm Nelson Amaral. I am a professor at the University of Alberta in Canada. The next speaker comes from Nanjing University. Jiang, right?
Oh, great. So yes, we have the presentation mode, and let me test. Oh yeah, great, yeah. Sorry. Yes, this is okay. Test. Oh, good. So today I to talk about the missing abstraction in teaching operating systems. So actually we had a paper on Usenix ADC 2023. Yes. You can check this paper later. So the basic question is that we, I guess most of the audiences are from architecture community, but I'm from operating system. So is there a better way to explain OS 101 to the next future generations of researchers that will do something big, like to make some binary translators to make RISC-V community better? So actually there is a gap. So I use this textbook, Ramsey's operating system 3 piece, is very good, nicely written book, but there is still a significant gap between the textbook and what we're doing research, like, or I'd like to publish a paper in the top conference of operating system. So the story begins with the definition of an operating system, right? Everyone knows that there is a body of software, in fact, that is responsible for making easy to run programs from the textbook definition. But actually, we have observed that students don't really know what is a program, but I guess both of us knows program very well. The sad fact is that at least 90% of students simply cannot understand. We have a formal semantics of the instructional set architecture, and there is a binary application binary interface, and it's well defined, and there is a calling convention which is also well defined, something like that. So I have a motivating example that everyone knows. I guess most of you teach this example or has been taught with this Table of Hanoi example, simple one, right? Move, you have n disks and you first recursively move n-1 to the third one, and then move one and move the rest. So very good. But even harder is that how many of you can provide a non-recursive implementation of this by simulating a stack? Right? Actually, this is a very hard problem, and I guess at least 90% of our students cannot write a non-recursive one before I'm actually teaching this style. So our goal is to let the students simply understand instruction set architecture, semantics, application binary interface, calling convention, something like that in an operating system course. So of course, the most important one, operating system interfaces. So actually, here goes our key takeaway message is that everything is a state machine. We all know that, right? We have a state, but actually students don't 100% clear understand what is a state and what is a state transition, because every stack frame actually has a program counter, and this is the time difference we all know very well, but the student do not. So if we do it correct, we actually can write a non-recursive one just like a recursive one. So state machine is the missing abstraction in operating system classes. So this is my point. So the first philosophy is that everything is a state machine, not only a program. So the computer system itself is actually a state machine, of course, right? We have registers, memory, CSR, and we can use instruction to control them. And actually, an operating system is a virtualized version of state machines. It's just a lot of containers of state machines, and they can pick up one state machine and advance it a little bit, or connect switch to another, something like this. And under this view, why this idea is interesting is that we can clearly define many things that maybe students have never thought in this direction. What is the semantics of fork? It's just a copy of the current state of state machine. Done. And what is the exact semantics for execve? It just resets the state machine to another binary. So we can do this clear cut. Actually, this is informal, right? I'm explaining it, but it gives students some inspiring idea that we can mathematically rigorously define this procedure, like what are the operating system interface, what are things happening in the operating systems actually. So we're also actually teaching students something like we're doing debugging, testing, something like this. We're essentially trying to observe the exact subset, of course, only a subset of the full state machine trace. Every single step of state transition. And we have to use profilers, we have to trace to have a simplified trace of this to find bugs, something like this. And we can also explain compilers, what are compiler optimizations, what can we do, right? It's like something like an eventual consistency. As long as the system call sequence under the same inputs remain the same, the compiler essentially can do anything. So this is exactly what we have done in the, not me, I have done, the community have done in the verified compiler like ComCert do for the formal specification of a correct compilation. So a lot of work on this line. So that said, I always talk to my students that when you have a problem, though there is no magic in the computer systems, everything is just a state machine. So you can think of the tracing profile, tracing process that you debug the program by every state transition and take some useful information, and you can resolve any problem in the computer system. And actually, I'm trying to solve a lot of interesting problems in the class too, using this idea. Yes. So the second one is that using the state machine abstraction give us executable models, right? There are state machines, so we can write emulators, like we always write QEMU or something for RISC-V. And yes, we implement a lot of emulators in different ways, like a full system emulator for teaching, like, sorry, this one cannot move. Yes, this is not moving, but it's a full system emulator that boosts Linux, RISC-V, and we can also visualize the state of a simplified operating system model, which consists of only, yes, this kind of system calls. We can model that in Python, and we can use the generator, the coroutine to implement them. And just all these system calls are sufficient for a very good operating system course. I can explain many things like there is a very interesting case in my courses. If you run this program, you will see 6 hello. Very okay, and you use paper and pencil, you say, oh, this will be 6. But if you get pipe this program to a word count, it says, oh, you get 8 hellos. So what happened? Right, this is because the buffer is also being copied on the fork, because the state is a verbatim replica of the state. And this is a little bit subtle, right? Because we have to model the exact buffer behavior to explain this case. And we can explain a lot of subtle cases like locks, like concurrency, for process-based concurrency, and a lot of interesting, since discussing a fork in the road paper, we actually can do with that model. And we can emulate. Then we can enumerate. We can exhaustively verify a program, at least to some extent. So actually, the emulator is actually itself is actually model checker. So we teach model checkers in the operating system course. So we let students know, oh, everything is state machine. So we actually can do some interesting tricks, and we can visualize the state transition graph, and we can verify the textbook cases like crash consistency. What will happen? As if you're encountering a system crash here, what kind of the file sim state will you leave, and whether they're consistent. And we can check that the textbook proof is actually, informal proof is actually correct. And yes, and we are able to teach something really non-trivial, like we can use a very naive state explorer. Like, okay, we can say X is chosen from any 32-bit integers, and Y can be chosen from any one of 32-bit integers. Then we get a state space explosion. Then the model checker will time out on this case, definitely, of course. Then students are clever to think of that. The tree, right? There is a state tree, state transition tree, and the tree will look like that the first layer of the tree has x equals 0, 1, 2, until the 2 to the 32 minus 1. So in this case, they're thinking of, can we do some clever trick that we can combine the state together? Then they invented the symbolic execution, right? This is exactly what we're doing using the path-based abstraction of the symbolic verification. So yes? Where's risk 5? There is no risk 5, right? Yes, there is, because we actually do not discuss any of the kernel implementation. This is the innovation in recent years. I guess from this year, I'm trying to do this. I removed every kernel implementation issue in this course. Because we can do everything, nearly everything in your user space. We teach virtual memory, of course, and we actually teach mmap, and we can use mmap to map shared pages to simulate the effect of virtual memory without knowing the kernel. And we talk about context switch, and actually we can do coroutines, right? We can implement coroutines purely on standard library, C library like set jump and long jump. They together with calling convention to provide sufficient power for context switch. And we also have a lot of fun. So we have more classes, so we can have a lot of fun at user service, including a game cheat or something like that. And there is only one special state transition when we're talking about what is the state machine. Is that as a process is a state transition system go by instruction. Then there's one special. This is the eCall instruction or the system call interface. And you close your eyes, and when you open your eyes, your entire address space is corrupted, right? Or modified by the operating systems. And yes, and actually also implies we can move everything. I can brought up RISC-V laptop to teach operating systems, something like that. So I guess this is run out of time. So yes, I'll keep the talk short. So this is the missing abstraction in operating systems. We have three principles. Everything is a state machine. And we can use the executable models to demonstrate everything. And we can actually use emulation and enumeration to prove something. And this takeaway message would be very interesting for the students to get the first contact of an operating system course. So we have the model tracker open, we have the paper, and maybe you have asked GPT to translate the lecture notes, but they're available also. So thank you. That's the end of my talk. Thank you.
That's very nice. I want to take your course.
Thank you.
Any questions? One thing that I was curious, you list here that you have your notes labs inside. What would be typical labs that the students do in this course? Like,
yes, we have a lot of interesting labs like hacking. We have originally we have a kernel lab, so they build a kernel, but we have an abstract library. Actually, the library is using the Xiangshan the core. Actually, we supported that. The abstraction, the abstract layer hides some hardware stuff, so students build on that layer, and that layer actually, I guess the first C program on Xiangshan. Actually, I ported that program, I guess. Okay, but I removed this the kernel lab this year, and we have something like we have a C read eval print loop. Normally we have Python, Scala, we have this REPL, but C we don't. But we can do dynamic linking, and we can compile that expression by calling GCC and load it into this program's address space. So this is a kind of interesting hack. And we get to implement the system profiler. System called profiler, but we pipe it to the strace tools to learn how to use pipe or inter-process communication, and a lot of interesting stuff. That's 8 or 10.
Sounds really interesting. Any more questions? Okay, so let's thank the speaker again.
Yeah, thank you.
You're next. Câmera para lá. Tem que ir pelo escape aqui, o que faz? Now we have someone from nearby. Sandro Rigo will be presenting from the University of Campinas.
Good afternoon, everyone. So I'm going to be talking about a little bit about continuous practices for RISC-V. And the main idea is to try to mix both the hardware and software domains, okay? And I'm an associate professor of the Institute of Computing in Campinas, University of Campinas, since 2005. And the ideas that I'm going to present to you today, they come from our experience in developing projects related to system-level software, simulators, compilers, and till 2023, we had in our university a project called the Mini Cloud, where we had a hack with PowerPC machines, and people from the open source community could validate their PowerPC ports for the several different open source softwares and the Linux Debian distribution, Grafana, and several of them that I can't remember by heart now. And the experience of building that and trying to provide a complete environment for continuous integration, and so people could accelerate the port of the software and the development. And we are now working with RISC-V. And the matrix extension for RISC-V is something that we are very interested in and following closely the technical groups from RISC-V International on that subject. And we are also thinking about how to accelerate the part of software and experimentation with this type of stuff. So I probably don't need this slide anymore because you'll be hearing since morning that systems are complex. You have a lot of software and a lot of hardware to develop it for RISC-V. And the importance of continuous integration and continuous deployment was already mentioned as well for some of the projects. And this is the standard method for guaranteeing quality for software nowadays. And every important software that you have in your Linux machine probably is hosted on GitHub or a similar platform with some kind of CI pipeline behind that. And people are starting to do that with hardware as well. So hardware design is done with HDLs, hardware description languages. And hardware is done by writing code. So why not use some of the established software tools and techniques that we have for guaranteeing quality to do that for hardware systems as well. Our keynote professor Bal, in the first talk of the day, mentioned objective-oriented programming-inspired techniques for his system. So for RISC-V, that's only a natural path because RISC-V is an open standard. You have a lot of different possibilities, and you will be having a lot of open source strengths coming from RISC-V. And many of the designs are already maintained on GitHub or similar platforms, okay? So people are starting to propose CI/CD-based methodologies for hardware on RISC-V and in different architectures. You can find a lot of papers for the last 5 years trying to apply the CI techniques for hardware. And at Unicamp, me and some of my colleagues, what we are interested in is how can we do that for hardware and software at the same time? How can we take advantage of these ideas in a complete ecosystem? So why is this important? You also already heard that from other speakers today. RISC-V is all about flexibility. You have a lot of different possibilities, different ISA extensions. You have a strong support from community. You may develop specific customization for specific domains. If you take a look at the RISC-V International website nowadays, you're going to see that we have RISC-V target automotive, HPC, AI, security. So imagine how many different RISC-V cores are going to be made available in the next few years on GitHub or similar platforms. How about software? How about software to support all those different variations of target applications? So the challenges. Take a look at the software stack. So this is just one example. A typical picture showing a software stack for an AI application. You have the application, some deep learning or AI framework, then you have libraries and runtimes, you have operating system, and hardware. Okay. Doesn't look that scary. Yeah, but this is kind of a 30,000 feet view of the problem. Try to deep dive and understand everything that's needed to put such a system running. And you may get something like this. Come on, professor, I can't read this slide. Yeah, that's the point. I can't do a slide that shows everything that's needed for that software stack. Okay, so there is a lot of components, software level components, system level components that are embedded in those layers. Okay, and this is just one example of application profile. This is an example that I took from a talk about HPC systems running AI. But RISC-V wants to excel in several different application profiles. So that's the challenge. The goal for RISC-V is to support well different applications. We need different software stacks. We need to be able to create customized software stacks. Better yet, we want to easily create customized software stacks that are performant. How can we do that? x86 has been around almost 50 years now. ARM was introduced in the mid-80s. First publicly released since that I found on the internet for a RISC-V course 2014, maybe a little earlier. Well, I couldn't get the date very clear, but it's around 2014. So one question that I had, how does that reflect in the software stack support? I convinced a student of mine that's here to take a look at this problem with me. So we decided to get software that are available on GitHub. We focus on the Debian distribution. Of course, it would be a lot of package to download and analyze, so it was not possible to do for the whole distribution. But we did for 8 different packages, system-level software, with one characteristic in mind. They all rely on assembly-level code embedded in the code, which makes them harder to port. That's the whole idea, all right? So these 8 different packages brought us this situation here. These are the numbers. If you count the number of assembly files available, summing up all 8 repositories, you see that RISC-V nowadays is in the 6th position in the number of assembly file already ported, let's call it that way. And you can say, well, like someone already mentioned, there is a lot of different architecture supported on Linux distributions nowadays. But RISC-V is already on the 6th position. It's not that bad, right? Yeah, but look at the last column. Compare RISC-V with the first place. 10 times more files for x86 than there is for RISC-V. So it's not that we are not doing the job. It's not that we are not doing well the job, but there is still a lot to be done. That's the message that I want to communicate here. There is still a lot of work to be done. And if you count number of assembly line code, we get 4 positions down, okay? And the difference between x86 and RISC-V increases in percentage as well. So we were trying to understand, looking at real software that are embedded in those software stacks, how we are doing today, and how is the gap? what's the gap that we have for the legacy architectures that have been around for several years more. Okay, that's the problem. What's the proposal? How can RISC-V catch up? The idea is take advantage of the experience. Why experience? Because many people that is working with RISC-V nowadays are the same ones that wrote the code for x86 in ARM, for starters. So they have been doing that for 20 years, 10 years, 15 years, 30 years, I don't know. But many people already have the experience that brought x86 and ARM to the state that they are now. And they are now moving to work with RISC-V. So this is an advantage. And nowadays, we have technologies that did not exist back in the day. So we need to take advantage of this technology, and some of them you already heard about in the previous talks as well. Okay? So we have cloud. We have continuous practice. We have AI. Okay? So x86 and ARM didn't have anything when they started, any of those when they started building the software stacks that are there nowadays. So we need to take advantage of those technologies and learning how to accelerate the development of RISC-V to close this gap easily. That's the idea that we want to explore at Unicamp. So what we want to do is to have a continuous practice framework that will mix hardware domain and software domain based on what you can get freely available on repositories on GitHub, both for hardware and software. Okay? So these are the main components. You need to have a pipeline that you can automatically execute, simulate, and verify cores. And you need to have, on the other side, a software pipeline that you can do the traditional CI development flow, combined with the possibility of simulating using FPGAs as well, because we don't have racks or full machines for RISC-V yet for testing all the software you wanted. So for now, we are going to be able only to use simulation FPGAs in some cases for in some situations. So for the hardware domain, we have another talk on Wednesday from my colleague, Professor Rodolfo Azevedo, who is not here today, but he's coming tomorrow. And I'm not giving too much spoiler on his side, okay? He's gonna show you what we already have there and up and running and accessible for you to play with continuous practice for RISC-V course on Wednesday. So how about possible applications from the software side and mixing both? One thing that you already can find in several works trying to do in the literature is using the combination of the idea of continuous practice with AI to extract information of what you are running, what you are simulating. And people have already managed to derive a specification for the hardware that is running in the simulation automatically using LLMs. So what they are envisioning is that this is very useful for hardware design, for people designing compilers, for people designing embedded software, and for trying to do compliance and certification. Because if you get a RISC-V core from a GitHub website, a GitHub repository, and you have test codes, you run, you can learn if he is really doing what the specification that is declared in the core demands from it. Okay, it's just trying to answer if your declared specifications match what the mined bonus, what I saw you doing while simulating or executing the FPGA. And then the system can ask, no, it does not. And what is missing is this. And this will accelerate the process of debugging and verification and certification, etc. So this is one idea that people is exploring in current works in the literature. And we can do certification in an incremental way. You can define levels of maturity for cores, for software, and create an automatic system that will attribute those levels of maturity depending on what we are able to run. Okay, so one core may pass through different levels of maturity during this life cycle. And you can think the same way for the software. You can do for both ways. If you have a stable core, you can test software. If you have a stable software, you can test core. You can cross the lines between both domains. And you can do that using different profiles. You can have certification for AI software stack. You can have the different certification for IoT software stack. You can have a different certification for security software stack. And the last one, the problem that I was motivated before, you can use that to accelerate the port of important software for RISC-V. So people is already thinking about connecting analysis frameworks that are AI-based modules to understand what is important in a piece of software, and you can map better which are the real important assembly codes that you have to translate for RISC-V to get the performance that you need. And you focus your expertise in those more important piece of software, and the easier ones or the smaller ones, you can even rely on LLMs to try to translate automatically. Okay? So you have a system that will help you improve the part of software that is very difficult to port by hand. So this is another idea that we tend to explore. So, to wrap up, in my opinion, to shape the future, the RISC-V community must embrace this modern continuous practice as a foundation for software, system-level software development, maybe, but targeting the whole software stack profiles, probably. And this will help bridge the gap with legacy platforms, and from that, reaching levels of excellence never seen before in the field. Thank you.
Questions? So you talk about automatic translation in the end of the talk now, right? Yeah. How do you do testing and verification?
How?
Oh, sorry. Sorry, I didn't see.
Small. A couple of years ago, we had exactly the same problem in making the ARM software for 64-bit ARM translated for from the 32-bit ARM to the 64-bit ARM. We found there were 1,400 files in the Debian distribution that had 32-bit ARM assembly language instructions in them that needed to go to 64-bit ARM in order to work properly. A lot of those we rewrote into C so that we wouldn't have to rewrite them again. A lot of them had workarounds for that already. So the other thing we found was there are applications that absolutely would have no sense on a 64-bit ARM, and in fact on any ARM, so having the assembly language in there didn't make any difference. For example, an application that would only run on Intel. So, you know, it's doable. We did it, and hopefully we got rid of some of the assembly language instructions in there.
Any comments on that?
Sure, there's a lot to be explored here, okay? We are starting with this direction for RISC-V, and you certainly can, like, raise from the assembly code and use the C, like you mentioned, and but those practices and those kind of infrastructure will help with that as well. Okay, that's our hope, not only for dealing with assembly level, but with all the levels, trying to accelerate to learn what is important to be translated or not. It doesn't matter the level, okay? So the idea is to establish a workflow that will accelerate the development in a whole. My examples were just examples where you could use those practices. Thank you.
Other questions? So then my question about the testing and verification of automatic translated assembly.
So this is the same problem that you see people from AI discussing, right? And what I saw, for example, last week I was talking about people from LLMs and discussing this type of stuff. They are starting to train LLMs to validate LLMs. So there are a lot of different ideas coming up to that. None is completely accepted by now, so it's going to be research. That's what I can answer today.
Any more questions? Yeah, there is one here.
I have some experience using Box 64 for running x86 binaries on RISC-V. And in my tests, at least, I've seen some kind of half of the performance of the native program with the same source code. With the same source code, the one in x86, the one built that to x86 was running like with half of the performance of the native, the one built to RISC-V. So I think this kind of layer that we have today to use legacy software on RISC-V. I think accelerating this, it's a better start than trying to port everything to RISC-V in a first moment, because I've seen an article in the Banana Pie forum of a guy who used RVV, RISC-V extensions to accelerate this process of translation, and he achieved 19% of the original performance. And I think, what do you think about these translation layers? You think this must keep existing, or you think you must create some recompiler that recompile everything to RISC-V, or do this manually? Or I think you understand what I mean.
So, if I got it correctly, I agree with you that this is useful, and it may be enough in several cases, okay? But when you're talking about having a really first-class, first-tier performance software stack for a big system, you probably need something that's native code, really well-written to achieve that. And how you're going to port that, well, it's up to you, but the idea here is try to accelerate the process of that. So what you described is useful, but not applicable in every situation. That's the short answer.
Okay, let's thank the speaker once more. And where is our last speaker? Come in, please. Goji Liu is coming from Peking University. Você pode colocar os slides dele aí? Não sei. in PowerPoint. So this will be the last talk of the section. And we have a panel later, I believe. We're probably going to have a little break in between.
Yeah, short break.
Yeah. Okay. So, go on.
Good afternoon, everyone. I'm Guo Jielo from Peking University. Today, I will share with you our work on the combination and mapping on the tiled reconfigurable architectures. Yeah, so it's not a new concept. In fact, we can find out some like example design dates back to the 1990s. So one example is the MIT raw architecture, as shown on this figure. And then after years, like it have a startup Tyera, occupied by EC chip, occupied by Mellux, and then occupied by NVIDIA. So this kind of architecture, I call it tiled architecture. But if we think about it as when we program the design, we may think of it as a reconfigure the core to another functionality. And then if we look at the FPGAs, in fact, the architecture also evolved gradually. It add in those tiled reconfigurable architecture. So on the right-hand side is how it evolved. At the beginning, every logic block are the same, and then gradually they add in the VRAM, the DSPs, the microarchitecture. And today, if you look at the AMD Versal ACAP architecture, we can find that it still has some reconfigurable logic region. So you can think of that as a big level network of lux and flip-flops, and it can emulate combinational and sequential logic. And besides, it add in an array. We call it AI engine array. So we can think of it as a coarse-grained world-level network of very long instruction processing elements, and it can implement the spatial and temporal data flow. And then it also has a network on chip connecting all these reconfigurable architectures. So in fact, if you look at the details, so it consists of a P array of very long instruction units, and each unit it can perform some SIMD instructions. And then for some cases, it can implement better performance per word and sometimes better performance per dollar. But of course, not on every workload, in some workload. And then we look at the processors. Now, this kind of architecture also integrated in the AMD Ryzen CPUs. So as shown on the left-hand side, the AMD call it the XDNA, comes from a Silex. So not only in the FPGAs, but also in CPUs, they all have this AI engine array. So how it relates to RISC-V? So of course, I'll tell some similar architecture, the Tenstorrent architecture that our keynote speaker at the afternoon also mentioned a few times. So this kind of architecture also one example of this tiled reconfigurable architecture. In HPE, it used 5 RISC-V core to implement the read, unpack, math, pack, and write operations, so that we can use this core to program it as different state and implement different data flow. And then in the remaining part of our talk, I will mention what we can compile and map on this kind of architecture. So this kind of architecture, we can decompose it into 2 layers. On the bottom is a single AI engine. So we write C code to implement the AI engine kernel. And in the upper level, it consists of an array of AI engines. So we can implement a data flow graph so to program this kind of architecture. So it consists of 2 levels of programs. One level on the bottom, and the other level at the array level. And then in the following of our work, we identify a few problems when we program this architecture. So the first problem is how we estimate the performance when we write a program on this architecture. And then we also identify some issues that exist, at least exist in the AMD's tools. And then at the end, we talk about how we can model the performance when we also consider the code transformation. So the first problem is the performance prediction. So performance model is important for the iterative flows. So we can think about different scenarios, one for the compilation parameter tuning, and the other for the workload partition, to partition the workload between the AI engines and the programmable logics. So I show two diagrams for the compiler tuning. We have the choices to choose what kind of compiler pass and what are the parameters for these passes. And it goes a loop to find a better parameter setting. And for the figure on the bottom, it shows a diagram for the workload partition. So because on no matter FPGAs or the AMD Ryzen AI chip, we need to partition the workload between CPU AIE or between the FPGA and AIE. So we have these scenarios that we may need the performance model. But if we look at what's existing performance model, AIE software simulator based on System C, it takes hours to simulate large applications. And of course, there are also some analytical model, but they use a lot of assumptions, and sometimes they are application specific. And other modern approach, they may not consider the characteristic of AI engines and AI engine array. So we need an accurate, fast, and effective prediction model. Before of the time limit, I just show our solution. So because at the beginning we show there are two levels of programming. One on the bottom level to program the AI engine, and on the top level we program the AI engine array. So we design a two-level graph representation, use the data-driven approach to learn the performance model. So on the bottom, we can get the control data flow graph of the AIE kernel code, and on the top, we can have another graph, the data flow graph. So we can construct this two-level graph structure to learn the latency when we write a two-level program on this kind of architecture. So we construct a data set consists of some 1,600 pieces of real code and 1,800 pieces of synthetic code as a data set. And we train the model, and we can find that we can achieve less than 2% error and over 1,000x speed up over the System C simulation. And there's some details on the training, but I just briefly mentioned that we divide the training into two stages. So first we train the bottom level, and then we freeze the parameters, and then we train the top level parameter. And then if we use on the two scenarios that we just mentioned for the compiler tuning, we can see that using our model, we can have the performance improve much faster than just use a System C simulation. And then for the workload partition, we can achieve the results in one example, 40% shorter latency than the AMD Vertex AI. Yeah, so this performance model we can achieve very low mean error rate, and then much faster than System C simulation. And then for some real applications, we can achieve shorter latency than using AMD Vertex AI. So this is one work that we done on this kind of architecture. And the second issue, so for the remaining two problems, I just briefly mentioned what are the issues. One is the utilization issues of this array. If we look at the recent publications, we can find that people already use it like for the weather prediction problem and for some machine learning problem. But the utilization of this AI engine array is relatively low. Like in this 2023 FPGA work, they only use 15% of this array. And if we use the AMD's White's AI, they only use 256 out of the 400 AI engines. So what may be the problem? So we analyze the utilization issues, and we find that the AIE compilation is a complex problem. Like we just mentioned, on the bottom level is a compilation problem on a SIMD structure with the very long instruction architecture, and on the upper level is a placement and routing problem of the network on chip. So the high utilization causes the routing congestion and failures. And we read the report. It reports that the failure causes because when the congestion is high. So some utilization of the channels over 200%. So to solve this problem, so the first step is conventional. So we transfer the code so that it can execute on this type of array. So what we've done is that besides the regular data flow, because all the data need to go through one kind of job called the programmer logic I/O, PLIO. So all the data, no matter how you program, it needs to go through the PLIO to the DDR or to the programmer logic. So what we do to avoid the congestion is that we use some algorithm to relieve the routing congestion. And then we also use the packet-based approach to avoid to reduce the number of PLIOs. So after we do this, we can achieve 100% AIE utilization, and then in some cases we can achieve 16% better performance than the White's AI. And of course, when we use these engines, better than the FPGA only solution. And the last work is on the also another performance estimation problem. So when we have a loops, we can do the schedule space exploration, and then for every schedule, conventionally we may need to map the schedule to estimate the performance, but this is also time consuming. So to do this, we also design another performance prediction. So instead of predicting end-to-end latency, we decompose it into a multitask problem. So we decompose the latency into 3 tasks. One task is the classification problem, whether some analytical solution is useful or not, is a Y0. And if it's not accurate, then we use 2 terms, Y1 and Y2, to correct the errors. So instead of training an end-to-end latency prediction model, we decompose it into a multitask model. So after we apply this model, we can reduce the prediction error, increase the map performance, reduce the mapped energy delay product. But of course, it has a cost. It will increase the mapping runtime, but depends whether the compilation quality is worthwhile or not. So it has cost, but you can decide whether we use more compilation time to trade for better performance. And at the end, we also work on some architecture evolution exploration problem. So at the last few years, we developed using some Chisel language to develop a package that can quickly generate this kind of tile reconfiguration architecture. And then in this flow, we can generate this architecture, and then there are 2 paths. The blue path is generate the hardware, and the red path that we can compile some data flow graph on this architecture, and we can emulate it on FPGAs. But this is still very time consuming, because every time when we change the architecture, we need to change the mapping algorithm. So what we are working on, this is in progress. What we are working on is that we are trying to also use the deep learning approach trying to find out some embedded in the latent space, and then we may use gradient descent or some generative AI to generate the architecture and the compilation code. So if we go through the upper path, we can implement a synthesizer to generate an architecture. And if we go to the lower path, we can implement a compiler to generate some compilation code. And if we work on both paths, then we can get some hardware-software co-optimization. But it's still work in progress. So to summarize, we discussed briefly the tau reconfigurable architecture, and we already see in the modern AMD CPUs, and also there's some efforts using the baby RISC-V core to build a tau. So as we mentioned in the tensorial architecture, in each tensor core, it consists of 5 baby RISC-V cores to do the work inside one core. So for this kind of tau architecture, we introduced 3 problems. One is the performance precision problem, the congestion-aware routing problem, mapping problem, and also the code transformation-oriented mapping problem. And in progress, we practice tomorrow's keynote speech, Professor Jiang's idea, large circuit model. So we are practicing his model to implement the synthesizer and compiler for this kind of architecture. And what I do not mention in this talk is that my other research project also work on the logic optimization and textual mapping for the EDA tools and also the dynamic RTL replication and security. But because of time limit, I do not cover in today's talk. So this is a summary of my talk. Thank you for listening.
Questions?
Thanks for your presentation. My question is, you were talking about graph neural networks, right? You start with that. People have used similar technology to generate graph-based databases.
Yeah.
How easy would it be to use your approach for graph databases? The first question. And do you use some standard format to feed the graph, like Neo4j or Tiger Graph or something, or you have a specific format?
Yeah, if I understand the question correctly, you are asking whether our architecture can perform the graph operation or
graph databases. I mean, some people have retargeted GNNs to graph databases in a simpler way. Is it how would be?
Okay.
How easy would it be to do that in your architecture?
You mean how we implement our performance prediction?
Yeah.
Yes, we just use the very basic one. So we use the pi geometric to implement this GNN. Not that complicated.
Okay, and my last question is really quickly. You have a ring of LPDDR4 memories around, right? Do you use the BRAMs inside the FPGA to do some caching? Do you need to do that?
Yes. Yeah, we can use the BRAM to improve the performance.
Yeah, so you do caching with the BRAMs inside the FPGA. Okay,
yeah.
All right, thank you.
Any more questions?
Hi, my question is on the utilization congestion-aware mapping, and specifically, how do you measure utilization in the AI engine, and if this is the max utilization that operation gets, or if it's 100% utilization with the congestion-aware mapping for the entire duration of that execution of that operation. Because 100% utilization for me, it seems, I just want to understand how did you get 100% utilization and when, yeah, that's it.
Yeah, that's a good question. So yeah, thank you for your comment. In fact, now my claim that 100% utilization is not that accurate. So whenever an AIE is used, I claim it as used. So if the 400 AIEs are all used, I claim it as 100% utilization. But in fact, if you look at the details, right, for each PE, it has its own memory, it has its own like ALU and VLIW. If you look at the details, in fact, it's still far from 100% utilization. But if you look at the other work, they are like much further from that utilization. Yeah.
Any more questions? Okay, so thank you again. Let's thank the speaker. Just a brief announcement. You're gonna need your budget for the dinner tonight, and you need your budget to enter the building tomorrow, so don't lose it. We're gonna have a break now for about 20 minutes or so while they set up for the panel. So, but stick around for the panel after the break.
Off. Retornem para seus lugares. Quem vai comandar aqui? Quem vai comandar?
Mr. Philip.
Mr. Philip, please.
I mean, you can take over as well if you want.
Sorry, you can.
No, this is great. I can see them. Okay. I just need my notes. Otherwise, I don't know what topics we have.
Another booth.
Yeah, that's perfectly.
Eu vou pegar mais pouquinho.
No, I can't see all of you. No, Alessandro now can get away without answering questions because Alessandro asked me.
Number one. Questions and you make the.
Yeah, we can do that too.
Agora sim. Ok.
Questions sound dangerous. The answers could be dangerous. So, welcome everybody to the last event of tonight. And actually, it's a pleasure seeing that the room is filling up for our panel. I have some panelists I don't really have to introduce because you've heard all of them speak today. But nonetheless, we have Andrea Gallo, CEO of RISC-V International, Marcelo Zuffo, professor at USB. So basically, he has the benefit of having his office here. Yungang Bao from the Chinese Academy of Sciences and the initiator and principal scientist, I think is the correct word, of the Beijing Institute of Open Source Chip. And Alessandro, I can't remember your full name, Capas, from the ministry here in Brazil, who's in charge of, well, a lot of the RISC-V projects, and he is also one of my fellow board members at RISC-V International. Actually, this promises to be a very interesting board because we have Dr. Bao is a board member, I'm a board member, Alessandro is a board member, and Andrea is our employee. So we talked a lot about RISC-V today, and one of the recurring topics really was regional innovation, technology, sovereignty. So RISC-V is really being set up and is really making headways as being an open technology that allows a lot of countries to reposition itself in the semiconductor value chain. So we educate, we build, but we don't just build what somebody else has defined, but we can innovate locally and have a real industry. So a general question, and feel free to take it in any order. So how has RISC-V facilitated this concept of technological sovereignty, the innovation in the various groups? And what lessons do we want to share here with the audience and globally about how RISC-V is changing the playing field? Who wants to go? I'll start with you.
Thank you, Philip. Well, thank you very much for everybody. Here is my first talk today, so I'd like to say thank you for commitment, people here to organize it, and welcome to everybody here in Brazil. I know a lot of people come far away trip for Brazil. So remember, when I goes to the China, it's the same. So yeah, yes. But thank you very much for all the people here. Wow. Like Philip talked about, the RISC-V is a huge opportunity for Brazil today. Some years ago, the Brazil passed by a very important initiative to try to support some kind of the manufacturer wafer here in Brazil. And of course, in the past, we can attract this kind of companies. And a lot of people here talk the Brazil lost the train of the innovation in the semiconductor. So when I hear this, I hear the train run in the circle line. So now you have the new opportunities, and the RISC-V is one of them for everybody here. Because that, the RISC-V could be an opportunity to the innovation, not only for the universities and academic solutions, but to the locally companies that work in here in Brazil. Just to know, Brazil have mainly two kinds of the companies working here. Most in design houses and packaging companies. So 40% of the ICs, memories ICs for the notebooks, computers, and cell phones manufacturing or is a package and testing locally in Brazil. If you think about the computers, only computers and notebooks is 80%. But this number is less than 9% that needs to Brazil in semiconductors. So we have a huge opportunity here because 91% of the local market needs to import semiconductors. So in this case, we try to work to bring more partnerships to not only manufacture here in Brazil, but to bring your IC design centers or your R&D centers in Brazil and working together with the Brazilian institutions and the Brazilian universities to start a new technological road to the future. So try to answer your question. For us, the RISC-V is a huge opportunity to promote new innovations in the startups and the huge companies here in Brazil, and to support the locally manufacturer here in Brazil. Brazil is the most bigger manufacturer of devices or final products outside the east of the Asia. So we need to increase this capability to support the locally semiconductors. So pass the word for my other friends. This is a word that I want to be there.
So, okay, so in China, RISC-V also brings many opportunities. And I think at least in three aspects. First is for industry, many Chinese companies, they currently more and more Chinese companies switched to RISC-V from ARM. Some company actually they already gain a lot from using RISC-V. I just give one example. There's a company in Shenzhen called Bluetram. This company is designing the TWS chips, the Bluetooth headset chip. So they used to use ARM, and many years ago, actually I think it's 7 years ago, they started to use RISC-V. But RISC-V is not just used for replace ARM, rather they use RISC-V for customization based on, according to the TWS program, since they analyzed the program and made a customization call. For example, like they used the compression instruction. They reduced the cache capacity, and so that the area of the chip is reduced and the power is reduced. And finally, their chip is the cost of the chip is much cheaper than ARM-based design. Then the chip, their chip has been, they ship the chip every year for 1 billion. Yeah, so the company got IPO, I think 3 years ago. I think so, yeah. So last year, they get a revenue of 1.8 billion RMB, and not a revenue. Revenue is 1.8 RMB, and the profit is like 400 million RMB. So this is a very successful story. This is because of RISC-V. So for industry, for companies, actually there are many these kind of companies. They get more profit, they get more revenue because of using RISC-V. So second is education. Actually, I already mentioned in my talk this morning, since RISC-V enable students to build their own design without licensing. You know, actually, almost I think 6 years ago, one of my students, he advocated that to build an open source ARM, and many students online, they supported him and would like to join the open source ARM project, but finally he get a warning from ARM lawyer. So because this is illegal without licensing, even they have the ability to build an open source implementation. So, but RISC-V brings the opportunity, and every student can build their own chip. Yeah. Finally, is open source efforts. Since open source already changed a lot for the development paradigm of software, and but without RISC-V, it is not easy to build the open source implementation. I mean, without open standard. Since RISC-V, it's just Andrew has stressed, emphasized that this is an open standard. Since open standard bring us more opportunities, we can do closed implementation, but aside closed implementation, it is enable us to design open source implementation. So that is also an effort China wants to invest in. Yeah. Okay.
Can I talk a bit? It's interesting how time flies. I was in the 4th year of the engineering course at the university here in 1987. It was in the peak of the Cold War. So we cannot import computers to Brazil at that time. We cannot import workstations, neither even instrumentation, parts and pieces of the instruments that we used to buy at that time used to arrive in Brazil destroyed. They used to use small hammers to broke the screen and things. That was 38 years ago in the first Cold War. And I was only 19 years old. I remember professor saying, you should design your own computer, you need to design your own oscilloscope. And we did that. Linux was still under developing. At that time, we wrote from scratch a kernel of Unix System 5, entirely from C. I remember Wilhelm was designing chips at that time. And at that time, we have very few architectural options. We have only Intel, AMD. We are trying to design Spark processors, but it was complicated. And then in 1889, the Berlin Wall finished. And in 1991, the Soviet Union collapsed. 1 month before the collapse of the Soviet Union, Linux was launched. We started to heard about Linux some years before. Some crazy guys, Mad Dog, for example, and that was very distant from us. And then suddenly we have a revolution. I remember that few years later, by 92, 93, we taking Intel computers and porting Linux for them. And then we start to build supercomputers using PC clusters. And unfortunately, at that age, we have the dominance of the Intel architecture. So we have only one option. I mean, PowerPC died, Spark died. So we have, I think, architectural Cold War because we have only one processor to play. That are the Intel microprocessors that we understand. They are not RISC, they are not okay, you know, but they are still around. And it was very interesting because meanwhile, we start to see such microprocessors entering in every domain in our day's life. We're not talking only about the high-end supercomputers, but we need to use microprocessors everywhere. I had a good conversation on Friday with the engineering head of a biggest German-based truck company in Brazil. The German industry is very strong in Brazil. And he told me that on a single truck, they need more than 2,000 microprocessors. So we are coming to the age where eventually we will be fully able to democratize the technology. And when I asked questions to Andrea, was about the full democratization of such technologies in every corner of the world. You know? Microprocessors, I have a mentor, Professor Alan Kay, who invented the laptop. He has a very famous phrase, if you're talking serious about your software, do your hardware. So I think that should be the vision. We are jumping on we are trying to build this global community on open hardware, open architectures, but we should understand, and that I learned with John Madog, that that is just the peak of the iceberg. Because we have already a very strong software, open source software community, and we need to combine these communities together. The message that I'd like to give is we need to think as a community from end to end, from applications to transistors. That's why I understand that the RISC-V is just the beginning. Of course, we are standardizing, we have an open standard for ISA, but I think we should go further. One of the most exciting messages that I received from Professor Bao was, well, there is a crazy Chinese professor that is opening a PDK in 55 nanometer. That, I think, is the future of humanity. But I want to stop talking here, but I'd like to give two aspects that are really important. We need to enhance the ecosystem, bringing together industry, universities, and government, and maybe investors. That's my current hat. This building here is the Innovation Center. So every day I talk with investors, industry, users, governments in all levels, cities, state. So I think people who are in here in this conference today need to be imbued by this community approach. Of course, on an ecosystem, we have collaboration, competition. But since our ecosystem is still not so strong in Latin America, I do believe that we should have more collaboration than competition. That is the picture that we need to observe in this region of the planet. That I mean, not only Brazil, but Latin America. And the second thing that is a very important message, and I will try to approach that in my keynote on Wednesday, we have a unique opportunity globally to verticalize the industry. If you take a look how we organize the industry in the past 40 years, there are the guys who do tape-outs. There are the other guys who do design. Other guys do ISA. Other guys do operating systems. Other guys do languages. Other guys do applications. I see the community organized in layers, and such layers sometimes doesn't have an appropriate discussion among them. I'm talking about as a professor on electronic systems. The guys who design processors, they believe that their job ends when they offer an IZA, and they doesn't care about software designers. I think that is a historical mistake on computing. We need to preconize co-design. From applications to transistors, we should pursue open source, smooth paths. And I was observing the lectures today. I think we're still behind of that. So that are my two messages. The ecosystem, let it strengthen, and each one in this room should be an ambassador of this ecosystem. And let's think about an opportunity of democratizing technology and have a full open stack from applications to transistors.
I would like to add one note. Philip, you mentioned the digital sovereignty as well in your question. I think countries have a duty of enabling their countries, their citizens. AI, cloud computing are pervasive in our lives, from phones to the cloud, credit card transactions, and these technologies shall be available to all the technical communities in every country. And so every country has a duty of enabling their citizens, their students, their engineers to access these technologies and be able to build innovation in all these areas. And not just depend on technologies that may come from other geographies. And I think this is what, Alessandro, you are doing here. You are enabling Brazil to have technologies that in the future will be designed and built here. And you are fulfilling a duty to all the Brazilian students and future engineers in being able to access the leading edge technologies. It's also a question of country security, because you need to protect the country from cybersecurity attacks and frauds and scams. So it's a very important role. And RISC-V here is an enabler block. RISC-V allows Brazil, because today we are here in Brazil, but the same is applicable to Italy, where I'm from, or anywhere else. RISC-V enables a country to build this knowledge and enable their citizens to access the technology and build new technology and new innovation locally in the country. So I think it's a very important task that Alessandro is fulfilling with the team, of course.
I like the most important phrase that I heard from, I know Andrea for a number of years, but he did a fantastic word today. I was expecting you mention again in your lecture. Now we can control our destiny. That's all about.
Actually, I'd like to dive a bit deeper on that topic, because Marcelo is so I'm Austrian. I exactly know how the Cold War played out because, well, we were transitioning from left to right, the goods, and when the Iron Curtain came down, it was not necessarily good for all parts of the country because suddenly we were no longer the trading post. So I can relate to what you said regarding access to technology under the Cold War, and there's actually something similar playing out today, and Andrea touched on that with controlling our own destiny because it's nation states trying to control trade patterns. It's also large multinational corporations trying to control trade patterns. And Dr. Bao, and this is a bit of a hot seat question to you because you did this project with BOSC and Xiangshan at a time when access to technology for China was being put into question. So how did the trade war, the access restrictions to some technologies impact your choices with RISC-V and Xiangshan? And on the other hand, how did it help you? Because you probably got a lot of government attention and support for your project, given that it was releasing China from that control.
Okay, so I think RISC-V is actually, RISC-V was born before trade war. So, yes. And I think before trade war, there are already many Chinese companies paying attention to RISC-V. You know, the first appearance in RISC-V, first appearance of RISC-V in China was in the year of 2015, or just 10 years ago. At that time, there a Chinese version of the position paper instruction set should be free, written by Professor Krista Asanovich and Professor David Patterson, and was published in China Computer Federation Communication in the year of the first issue of the year 2015. So since 2015, more and more Chinese company they noticed the RISC-V, and many universities, like for example, like my institute, ICT, Institute of Computing Technology, Chinese Academy of Science, already recognized the potential of RISC-V after the year of 2015. So, you know, ICT was the founding member of RISC-V Foundation in 2015. So at that time, we all recognized that RISC-V has the potential because of the openness. Since the instruction set over the past decades, almost half a century, ISA all belong to companies, yeah. But RISC-V is different. This is an open instruction set. It is open standard. Since this is open, then it brings us a lot of opportunities, enables like education, enables customization, and so forth. So that was all the stories before trade war. You know, I think trade war just make people be aware of the importance of openness. Since we can see, we realize that it is only open source can mitigate the negative impact of the trade war. Since open technology, open source, this is kind of across the boundary of different countries. So open source can gather people from different countries, different regions. So that is why I think the Chinese people, Chinese company, even the Chinese government realized we need a open source to unite more people from different regions. And that is also why we get more support from Chinese company and Chinese government and so forth. Yeah.
So for China, the story started before, and I'm certain it helped a bit with getting funding. But now the question, Alessandro, Brazil joined RISC-V after the trade war. So how did this global tension to trade war affect the policies here in Brazil, or was it just coincidental?
Well, you know, we joined after the trade war, but since more than 5 years, we can see the problems about the sovereign technological here in Brazil. So we're looking for all the time more restrictions to access the semiconductors, like Professor Zufo talked about. I'm working a lot of years ago in the aerospace industry here in Brazil. So when I see the satellites launching in the Europe and US using the last technology for us to access the more older than 10 years old processors is a very, very, well, problem for us. So in this case, we try to thinking about the strategic for the government. And this strategic is not for the government, but this strategic for the country, okay? Because this strategic needed to pass through all the governments. We need to make some kind of invest, because in semiconductors, the invest needs to be perennial, is continuous. So, and of course, the technologies run away, so we need to make an actualization. Because that, we launch a lot of other projects here in Brazil. So the projects with the human resources. Other countries needs to be your own human resources. And in our own programs, like the Secretary Henrique told us today, the idea is to put more 4K new engineers in the next 2 years in the market. Not only to attract the companies, but to provide the locally, and of course the partnerships that want to be here, a capability to design in Brazil. This is a very important, design in Brazil. Not only the manufacturing in Brazil, but the design, the capability of the brain needs to be here. So in this case, this is a very right decision to access the open source and the open community, because the first one is not only the open source, it's the open community. The community that wants to be cooperative, to be partnership. And because that, I appreciate a lot the person of Professor Bo here and all the peoples come China that could be here in Brazil. Today morning we have the sign official, the MOU, the cooperation between the local association, ABSEMI, and the RISC-V environment industry in China. This is another point that you need to looking for. Not the trade war is a problem only for the trade. The trade war is a problem because they separate the peoples. So when okay, thank you. So the idea is after the trade war, we need to make the bridge. So the RISC-V is an opportunity to us because in RISC-V we can find friendlies and partnership with the China, with the Europe, with a lot of companies in US too, because the US is not the government, the US is the people in the US. So we have a very good friends in US. But in the case of the China is very closely to Brazil and friendship. And when I arrive in the China, it's a very pleasure to be there because the citizen, the people, is a very similar. Not, of course, I have a lot of friends in Europe, okay? Don't worry about that. Yes. Yeah, that's good. But the idea is to promote more collaborative projects, more collaborative partnership, working together, and RISC-V could be the key for Brazilian goal, and not only Brazil, but Latin America too.
So actually, I need to repeat a few things you said because they are close to my heart and they are really important for RISC-V. So when you positioned RISC-V as something that transcends the trade war, so yes, maybe a catalyst for all of us to get more funding for RISC-V, but we also have to ask ourselves, as you said, what comes after? Trade war never lasts forever. Governments change, politics change, and RISC-V, because we can, even in decoupling, continue on it openly together, but also separately. We're building a technological foundation, really, for what comes after the trade war and the decoupling when we get closer together. Andrea, you want to jump in? Go ahead.
I want just to reinforce the message that RISC-V is not a way of bypassing trade war. RISC-V is fully respectful of every country's. RISC-V as a specification is a public industry standard, and as such it allows to develop technologies in every country. But RISC-V is not an implementation, is not transferring technology. Just to ensure that we don't have any confusion here. It's an important distinction.
That was actually a good point. So RISC-V allows us all to work on something and prepare for what comes after, but at the same time it allows us to do that because it is a specification. It is a standard. And international standards are used to facilitate global trade and not to erect barriers. And that's really at the heart of the RISC-V idea. You've all already been touching on the next topic, so I couldn't resist going into the political topic into trade war. It always gets the audience captured. But Alessandro already touched on it. The other thing he said, and that was very important to me, is he said you were doing things as a design house and then manufacturing, but that was the end of the value chain for you. So with RISC-V, with doing more in-house and manufacturing and going up the value chain, you're actually realizing an opportunity for Brazil. Just as Andrea said, everybody needs to look after their country and their region. And that brings up a question because already in the introduction, Jiang, you said that this has realized a lot of value in China. So how do you really see RISC-V and what you've been doing over the last 5 years, 10 years, contribute to the growth of the semiconductor industry in China today?
Yes, I think in China, the RISC-V is, this is quite interesting. This is a bottom-up way. And so the contribution is also, I think the most important part is we make the whole ecosystem grow. Yeah, this is how to make the RISC-V ecosystem grow. This is the most important for everyone in the community. So, but in China, I think I want to I want to share some the story of how Chinese community involved in the community. So actually, this is a bottom-up way. It's quite interesting. First, many Chinese company they noticed the RISC-V and they switched to RISC-V from ARM, and then the local government they paid attention to this phenomena, and they found that why there are so many companies talking about RISC-V, and then those local government they put forward some policies, local policies, to attract those companies to open up sites in their cities. So this is a very common in China, because there are competition between cities. The different cities they will put forward policies to attract companies. Since many companies are aware of paying attention to RISC-V, then the local government will pay attention to RISC-V. And then for a couple of years, then I think finally it's the central government started to invest on RISC-V by open source and by the RVEI, this organizations to help coordinate the efforts between local governments, between central governments, and also provide more supports for companies. So I think this is the way how China involved in the RISC-V community to make the whole RISC-V ecosystem grow. Yeah.
So thank you for that background. This may be an odd question to you, Marcelo, as a professor, but you mentioned you're spending a lot of time here in the building talking to investors. So what is the role of RISC-V and of what you do with RISC-V in developing this economic value? So if you're talking to investors, you're probably talking about RISC-V. Can you give some background on that?
Absolutely. Well, one underlying value proposition is the agility. In the process of democratizing instruction set, we expand the range of opportunities, and basically we break blocker walls. Because before we have only one architecture to play, and now we have other possibilities. The process is quite similar to what happened with 3D printers. Before 2000, all 3D printers are closed, so we cannot design our own 3D printer, despite the technology was super well known in the scientific literature, because one company, I cannot mention the company, has the patents, and no one can play with 3D printers. And now you see 3D printers everywhere because these patents gone. We have full access to low-cost microprocessors, and we have language standards like G-code and STL. So you can see that everyone here, everyone in the planet is designing and manufacturing 3D printers. So the fundamental question is the value proposition. Still, demand is a problem. So talking with investors, we still have a barrier of access that is the tape-outs, easy access to tape-outs. It's a different context in China. I learned today that you guys have a lot of plants there. We don't have any tape-out plant in Brazil. So that's a sovereignty problem because we need to send our designs abroad. And I should say that most of the times we doesn't have the same priorities. I talk a lot with US universities. I'm introducing my courseware agility, IC design agility. So from scratch to application, we are claiming that we can design a ship in 12 weeks. But when we try to tape out then, even when we have money, for example, our poodle that we announced today is delayed 1 year, right? Because we do not have, despite we pay for that, we doesn't have the same priority in global foundries, not the company itself, but access to the global foundries. So that is a problem to local investors because they said, well, time is market. Time to the market is an asset. But at the same time, Professor Bao shared his vision about we're doing a bottom-up approach. So if we have the sense of community and we start to collaborate, the robustness of the ecosystem is also an asset for investors. Because in the end of the day, they said, okay, I will invest this, I will have this wonderful microprocessor, I have a business model for this demand, and then people, can I have engineers in Brazil? And that's usually, I see several professors in the audience. We know that we have a very good, talented community here, but then we have the diaspora. Since they doesn't find jobs in Brazil, the one problem of our designers that they will start to seek jobs abroad. I travel across the whole globe, and I met Brazilian engineers at Intel, Infineon, ARM. There is an ARM Brazilian community there, everywhere. So that is why it's so important having guys like Alessandro. There is a unique particularity in Brazil that nobody knows very well. You go to USA, you talk with technicians there and here. Few people knows that Alessandro has a PhD in semiconductors, Mr. Alessandro. So all guys that are in our ministry are high-ranked former scientists. That is very important to define a public policy in the country. The problem is not Alessandro, is not Enrique, but the problem is the guys up here, you know. But again, if we have the sense of community and we support these guys and we deliver, I think time will fix everything. But it's a very difficult question. There is a super resistance from even local industry that consume microprocessors in Brazil. Just to give a glimpse, Philip, our trade deficit in electronics in Brazil is $50 billion. Probably 2/3 of these equipment have microprocessor embedded. Why not we substitute some of these microprocessors by local content? No? So we need to help Alessandro and Enrique formulating policies where we can substitute this massive amount of electronics imports by local content. And that is heavily dependent on public policies and also our Congress.
And I just realized something very important also for Europe. I think our governments would work much better if we only elected people that have at least a PhD in physics. So that's generally a thing. We need to not have that just at the ministry, but on the top level that would help too. But all joking aside, Andrea, very tough question because they've all been talking about how it's going to benefit the regions if RISC-V is successful, taken up, goes through the curriculum, investments. What is RISC-V International doing? So we're one global entity, but are we actively pursuing opportunities? Do we have policies, programs to enable the regions to actually build things up and get their benefit out of RISC-V?
We have activities in coordinating the communities and the academia. So growing the seeds across all the geographies. So one example is the mentorship program. And for example, Rafael here has been driving it very successfully. Another example is the hackathons that we organize. We organize hackathons in person at the summits, but also online. And online hackathons means that engineers from wherever in the world can participate. We also have an ambassador program where the best talents get recognized as contributors and evangelists of RISC-V. And again, this is to help deploy the knowledge as much as possible through all the academia. I think one of the challenges is for us as the RISC-V staff to scale and be present to as many events as possible. And so one of the ideas is to leverage this concept of the ambassadors to be official representatives for RISC-V at all the events.
Well, I was hoping that something like global investment fund for new RISC-V startups was in the making, but it was just hope. Then again, you touched on an important subject. I've heard it a couple of times already today, which is workforce development. So RISC-V is an opportunity. So it is open. It's not controlled by one company. It's coming out of academia. We have textbooks about it. We've seen it today, many learning resources. So it seems to be an ideal platform for developing the next generation talent, because semiconductor design, software design is really a question of manpower, talent. Brazil has a huge advantage here, given the demographics with a younger population, many new graduates coming out. So my question to all of you is, so how are educational policies, how is what your institutions are doing, and how are government policies affecting workforce development around RISC-V? And how is RISC-V an opportunity for what you're doing in your institutions to develop the workforce of tomorrow to actually realize this economic benefit? So I'll start with you, Alessandro, because it's a very political question.
Yeah, no, very good. Yeah. Well, here in Brazil, we're working with the National Strategy for the Semiconductors. This strategy is founded by 4 pillars. The first one is the human resources. The second one is the regulation and the incentives, fiscal incentives. The third is the R&D. And the last one, 40, is the financial support. So in case of the first one, when you're thinking about the human resources, each one know about the IC designer's plan that you intend to put the engineers on the market, but this is not only the one actions that we're doing. We're working a lot with the SCB Micro, the Brazilian Association of Microelectronics. A lot of people here come from SCB Micro to support access to the universities, to some partners with the EDA tools, scholarships for the students, and multi-wafer projects access to the prototype in your designs. But this is not only, we don't make my job in the last phase. We need to bring more early. So this next semester we will launch the locally competition for the fundamental schools to bring more students to the engineers and the semiconductors. This project will be launched to access the fundamentals and the undergraduate students. So this is idea. And another actions is to provide support for the graduations and masters and doctors projects with the scholarships, with the internship, with the partners. I talk about the Professor Bao, how you can exchange students in China and Brazil. So it's very closer to be there. So, but this is in the point of the human resources, is the first one. The second, like I said, is the regulation. We increase the locally regulation to be more modern, fiscal attractive to the companies working here. We have the program named PADIS, the program to support the semiconductor industry in Brazil. And so when the companies goes to Brazil to manufacture or design semiconductors here, they have a very huge package of the fiscal incentives, and otherwise they need to invest 5% of revenue in R&D. So this R&D is now in the last years is provide a very good money to support the universities, the projects and ICTs and RTOs in Brazil. The third is R&D. R&D is very important because R&D, we can see the special areas in Brazil, like you know, the environmental is very important to us. The agricultural is very important too. But we're looking for the robotics, industrial solutions, automotive, energy, next energy solutions. So in this case, we're looking for the projects, not only in Brazil, but the cooperating projects using semiconductors that could be provide some kind of solutions in these areas. And of course, the last one, the money. The Brazilian government now, of course, last year we launched a new project named Nova Indústria Brasil, the new Brazilian industry. This project has come from the National Bank of Development and will provide 26 billion of reais for one actions to advance the locally manufacturing in Brazil. And semiconductors is one of these industries that could be provided. Today morning, Mr. Rogério signed the MOU, and the company from the Mr. Rogério is Zilia. Zilia is a company with partnership with the Chinese group, and in this case, they are investing now in Brazil plus something like 400 million reais capped on this kind of funds. So I think it's not only one actions, but we need to make an strategic for the country, and this is our idea about that.
Thank you. Wonderful summary. I'm about to ask you, Dr. Bao, but first I would like to hear Marcelo with the other side of the Brazilian story. So on the one hand, whether you're happy with all the money that's flowing in, but also how is the university side playing out, so workforce development to support exactly that initiative?
Well, particular at this government, we never had so many resources like we had before. We are having a fiscal crisis, and together, as a democratic country, we fought together, is what I call the triple helix. So ABCM, university, and government, we work in the Congress. So our science and technology budget is not under the possible funds that could be cut by the federal government. That, I think, is a big victory. And then we have a very professional ministry try to orchestrate these funds under national policies. So we protected, we shielded our national science and technology budget at the Congress with full support from the executive. So from this point of view, despite the country is quite asymmetric, I think we should say that we're trying to do the best to make the money flowing. And as a researcher, I can say that in recent years, we are never happy, right, Alessandro? But we should say that we are not on a bad shape. I see guys working. I see by the number of PhD theses and papers I'm finding Brazilians in our conference. I remember that 4 years ago, we even have money to pay for our conferences, right? And the situation is completely different. But that doesn't mean that we have problems. I have 3 thoughts about education. The first one is the red flag regarding engineering education in Brazil. In 1 decade, we lost 24% of engineering seats in universities. We decreased from near 500,000 students in engineering to less than 350. So we have this red flag, and it's all about our children. We will not revert this process in the short time with short-term policies. Need to be long-term. And then that are the things that became interesting on RISC-V. Because before RISC-V, my research group, particularly my wife, she worked in the $100 laptop. That was a completely failure. Why? Because the hardware was not open source. So the big debate among educators here is not doing the real thing, that is digital literacy on young people, but transforming these kids on consumers of a given technology that at that time could be green or blue. Because some time ago, microprocessor brands or ISA, they have colors. So remember that. So because that bring to the community a huge, a massive ethical debate, a war about the necessity of having neutral platforms. And when we talk about open hardware, we are talking about a neutral hardware platform that is not captured by a company X, I, and Z. And then that could be the perfect platform to educate our children. Thinking about that, particular USP, on an undergraduate level, we are promoting neutral technologies for digital literacy. We have a website named Code.IoT that reach already 250,000 kids. 250,000 kids. Now, since last week, we have our open hardware. So one of our plans, especially on our RISC-V Poodle, is teaching kids AI programming on a neutral platform. Time will say if you are in a correct or a bad situation. One representative from the Ministry of Education is visiting me this week, talking about we manufacture deploying 1 million boards that now are not $100, but they will cost something like $5 in Brazil. And secondly, we need to promote, when we talk about the ecosystem and the community, we need to think about the future generations. So John, Liza, they are talking about the hackathons for kids. So we have this idea of using our low-end RISC-V boards to do massive digital literacy programs into this country. We have the Code.IoT platform. We have partnerships with Brazil is a federation with 27 states. And now state secretaries for education are very excited about this perspective. So we have other ideas about how to massively promote such technologies on a short term and a long term. Unfortunately, on a long term, as a democracy, we need to create what we call long-term policies that sometimes are complicated when we have a presidential scheme where president changes every 4 years, and president in Brazil has a lot of power. So some policies can change radically, maybe in 2 years. And finally, I think I will insist again, RISC-V is what I call a neutral, non-blocking technology that can accelerate the time of the market. So I'm trying to convince my students in the 4th year at the School of Electrical Engineering that they can design a full microprocessor running software in less than 12 weeks. Professor Jiang Rabai from Berkeley, a close colleague from David Patterson, Ian introduced me to Luca Benini. He's claiming that we need to promote agile RISC-V courseware. And finally, I'm talking too much, but I finalize here. There are some people with this vision that maybe in future, with this revolution of open sourcing hardware, we will be capable to design 3D printers that will print out our microprocessors in maybe 10 years. That is just a vision that my research group incorporated. This morning, John gave me the book about Mr. Gerber. Mr. Gerber was the inventor of, he gave me a precious book that is the biography of Mr. Gerber, the guy who invented the Gerber files. I cannot imagine that Mr. Gerber imagined how we use Gerber files today. And that's all about the democratization. So I really believe that in few years, you have a 3D printer, you press a button, we will have more hair or not hair, but I think these things will happen sooner or later.
So we're already losing our audience, so I'll try to get quickly through that and cut it short a bit. Dr. Bauer, I know you could probably talk for an hour on the topic of education and how it's been evolving for workforce development in China. But what are the highlights that you see? So you have the OpenChip initiative, which is exciting, but how does it work downstream? So the engineers that you are educating, are they being picked up by the market, and what is the effect that they have on the companies they work in?
Yep. So just I mentioned there are more than 10,000 students participating in the 101 Chip initiative, and almost 2,000 already finished their tasks, and most of them are still pursuing their master degree or PhD degree, and some of them already go to job marketing, and we did a survey about where they go and how about their performance in their employee companies. So we found out that most of them go to Huawei, yes, Huawei High Silicon, and some in China there are many.
So that's the reason why Peter was.
Oh, why Peter is here? Yeah. Huawei attracted the most students who finished the One Student One Chip initiative. Yeah, Huawei number one, and so they also, those students go to different companies. But I think since I believe Huawei's standard is probably is the highest standard among most companies. So I think the quality is actually ensured by Huawei. It's kind of qualified by Huawei. So I think this is currently the survey. The result by the result of the survey. But but still in China, besides one student one chip initiative, there are other efforts for RISC-V education. For example, there are already some textbook about based on RISC-V, and there are some competition, the national-wide competition for RISC-V track. So this national competition for undergraduate students who those awarded students, they can get extra points when they applying for graduate program. So I think these efforts will encourage undergraduate students to study RISC-V related courses. Yeah.
So thank you. And in order to close that out and not keep people too long away from their dinner, just one last question to all of you. And I think we'll go this way around so that Andrea gets the last word. I would just like you, in a few sentences, very briefly state what are your personal strategic challenges and opportunities with RISC-V. So from your job at the ministry, from your positions in China at the CAS, at the university, and of course with Andrea, what are your strategic challenges and opportunities for RISC-V as CEO of RISC-V in the end? So let's start with you, Alessandro.
Yeah. Well, I think the key issue about the next generation is the human resources. We don't do anything if you don't have the good human resources with high knowledge and the capability not only to make a technical design, but to be an entrepreneurship. Not entrepreneurship like make your startup, but entrepreneurship could be improving your own company. So I think is the human resources is the first and the last one.
Thank you.
Okay. I think China is a big market. So in China, we already have many commercial companies, but there are still two important open. One is open source technology. So we need to provide open source technology to the whole industry, and so that to reduce the total cost of the industry. And the second open is open market. Since China is still, actually the government actually is always emphasize that the Chinese market is open and welcome company all over the world. So you will find you will see there are many like RISC-V companies all over the world, like Sci-Fi, like Torrent, and they also have customers in China. So I think this is a healthy way to promote RISC-V in China. Yeah.
Well, I think that is the beginning of a long history that we'll design in this country. I think government entering in the arena give us a lot of robustness. I truly believe on the triple helix, government, universities, and companies together. We need to have success cases. We need to have in Brazil, the deficit is enormous. So we are purchasing per year 50 billion in processors and microcontrollers. We need to have some success cases. I think when we start to perform in such way, I do believe that RISC-V, it's a exponential technology. So sparking the process, eventually we can spark the exponential. I think it's just a question of time.
I think one challenge common to all ISAs, not specific to RISC-V, common to all colors, yes, is reducing the time to value add. I'm looking at companies that need to develop products that will go in mass production. When they receive a development kit, the support of the documentation, the support of the kernel, make files, tool chain, is never ready to go. Yeah. It takes weeks, if not months, to rebuild the kernel that you need with the tool chain that gives you the best performance or code size, with the libraries that you need for your project. So it takes months before you can start developing your product, so adding your value. That is what you will make money on, is your value add. So reducing this time from the moment you receive a development kit to the moment you start adding your value, time to value add. Reducing that is critical, and that is a challenge for all the ISAs. The opportunity with RISC-V is that by working all together as one single ecosystem, and working with the mindset of working upstream first and not in silos, but working all together, sharing what is common, that is non-differentiating. Sharing that means that then when you get a development kit, my dream is that the same day you will be able to start developing your product.
I have a clear example. 19 March 2020, the start of the pandemic in Brazil. I was in my office, a professor came to me and said, Zufo, we need to design ventilator, otherwise thousands of people will die. And we need to do that quickly. I said, oh, great, I never saw a ventilator before. And then he came to me and asked, do you have these Labrador boards? Do you know every transistor on it? I said, yes, we designed it. Great, deal. 100 days later, 100 days, we certified the ventilators in our national agency. And then we started manufacturing. What maybe the biggest conclusion is what Andrea said. If you know every transistor in your hardware, the time to the market is the value. And that's all about having open source ISAs. I'm sorry to interrupt, but that is an incredible and maybe the most important conclusion of the day.
So thank you also for this inspiring story. I remember the news reports about the Brazilian ventilators, by the way. That was quite a feast. And yes, it goes back to zero-day enablement and controlling your own destiny, what we've all talked about. And this is what will allow all of our countries to climb up the semiconductor value chain, one step after another, and thanks to RISC-V. And with that, thank you all for listening today. Thank you to the panelists. It was an exciting conversation. We will continue this workshop tomorrow, and I hope that I'll see most of you again tomorrow for another series of exciting keynotes and presentations.
We have the dinner now. Elena, are you in?